In this video, we're going to calculate the standard deviation of a single season of NFL. I'm going to ask you to do it for many seasons and for another league of your choice. Now, this is a very simple thing to do. It requires really less than a minute, but I'd like to take this opportunity to talk about some data issues that are common and introduce some more commands that you might find useful going forward. First, I want to show you that this data comes from an Excel spreadsheet. Now, I obtained this data simply from copying and pasting tables of information from NFL.com. There's going to be many issues with doing that, and so this should be a good exercise to show you that you always want to try to find your data sources in a clean format, already provided, hopefully as a CSV file, not Excel, and to show you some of the issues with copying and pasting data into Excel before importing it into Stata. The first thing you might notice is this home and road record looks kind of odd. And the problem is Excel always tries to guess what the user wants to do. It thinks it knows better than you and automatically formats your data. This is one reason to avoid Excel. It's constantly doing things for you, assuming it knows what's best. And what less would you expect from a company founded by Bill Gates? So here, the New England Patriots is on the second row, and in this season they went 14-2. Their home record was 6-2, their road record was 8-0. When 6-2 was pasted into the cell, Excel decided that that was a date. That was June 2nd. Likewise, when 8-0 was pasted into this cell, Excel decided that was August of 2000. Good luck disentangling these and figuring out what the real data was. Another issue is if we try to reformat these columns, perhaps we want to go back to general or maybe just say text. When you format columns in Excel as text, it displays exactly what you typed, which is what we should have done in the beginning. But notice if I do that now, it gives me these weird numbers. This is the numerical representation of the dates that Excel was displaying. So it's already converted your raw data, and there's really no way to get it back that I'm aware of. Now, a better thing you could have done, or I should have done, is start with a blank sheet if you have to use this method of pasting into Excel. Click the upper right corner to select the entire sheet. Click Format Cells. And before you paste anything, tell Excel that you want them all to be text. When you do that, whatever you paste in the cells will appear as text. It will appear exactly as it was typed. So if it's a 6-2, that's exactly what will show. I'll give you an example. I'll just type it here by hand, 6-2 or 1, and it stays that way. If I do 8-0, it stays that way. Now, of course, this will take up more memory. Text takes up more memory than numbers, which isn't such a big deal if your data set's small enough to be on an Excel spreadsheet. But once you import it into Stata, you will have to destring the numbers and tell Stata that those shouldn't be strings, they should be numbers. But now you know how to do that. Okay, moving on. How do we import this into Stata? Well, the command is called import, and the way I do it is I go to File, come down here to Import, select Excel spreadsheet, because in this case that's what we want. Typically, I like to store data as a CSV, but here we have an Excel sheet. It will bring up this window where you find the data, and once you find the data, it displays a little preview here of what you should be getting, so you can make sure it's what you expect. Now, the one thing I noticed that I don't like here is the first row is actually our variable names. We want those to be up here. I don't want to call the variables A, B, C, D, and so on and so forth. So what we do is we use the option first row, and I click import the first row's variable names, and now you see they're displayed as the variable names up top. We have some options. We can import all the data as strings, and you might think that would fix the issue here, but again, the formatting has already been done. If we do that, this will import as 2-June, or actually it might import as those numbers, but in either case, we're not going to get the raw data back, so that doesn't help us here. For the variable names, we can preserve the case. As you can see, NFL and T are capital, the rest is lowercase. If I choose preserve, it will preserve that case. I can make the variables all lowercase or all uppercase. Now, sometimes in the past, I have chosen to import all variables as uppercase, And then variables I make are all lowercase. That way I can always tell while I'm working on something if the variable is a raw variable that came from the data or if it's a variable that I created. I don't do that so much anymore, but at one point I found it useful. In this case, we'll just preserve the variable case and make changes as we see fit. Now lastly, sometimes you don't want to import an entire sheet, and if that's the case, you can actually click this option here and say exactly what cells you want to import, so you can give it a smaller range if you want. Here we're just going to import everything on the sheet. So I click OK, and Stata writes the code for you, so we could have just simply written this code by hand. As you can see, it's quite long, which is why I typically don't do it. And it informs us that 21 variables are in the dataset, and we have 320 observations. If you're familiar with your dataset, you want to check this information and make sure that's what you expected. Now, also over here, we have the review window saying exactly what that code was. You might want to copy and paste that into a do file or get one started. And one thing you can do is right-click it, send to do file editor, and it opens a new do file editor where it copied that for you. Now, I find this feature to be very useful. However, if we continue to write codes and then select them to copy over to the do file, it'll open a do file every time we do that. So, unfortunately, I don't know a way, as of right now, to copy commands in the review window to the same do file. You would have to select them all at once. But this will get us started. And just for good practice, I will write here a note that says what do file I'm creating. Here we are calculating competitive balance measures for NFL. Okay, going back to Stata, let's take a look at this data. So it looks just like it did in an Excel spreadsheet. These variables in yellow were imported as strings, as they are. The variables in white are numbers. And once again, we have this issue with the home and road records being incorrectly interpreted, as well as the division. But you notice here, instead of division, div, the variable is just the column n. What's going on there? Well, if I look over here, I see that there is a division variable. It's the third one. So scrolling back, notice that we already had a variable called div. So when Stata comes across the second one called div, it can't name it the same thing. It just gives it the column letter. This is another issue with Excel. If you have many variables with the same name, Stata is not going to let you do that. And rather than assume what you want it called, division 2, division 3, and so on and so forth, Stata will just not give it a name. It'll give it the column name that it came from. And then you're going to have to change that. Luckily for us, we're not going to use these variables, so I don't have to fix them. We can ignore that. Really, the only ones this far over we care about is year, which tells us what season we're in. So actually, to clean things up, I might want to just drop all the variables we're not going to use. So I will look at our variable list, and I will go ahead and drop all the ones we don't want to use, and I will just click them rather than type them. We're not going to care about division. Points for, points against, net points, touchdowns, records, we don't care about these. Just year. So I can click all those to drop them, or since I dropped everything between, well, I dropped division and then everything between points for and last 5. A more succinct way to do this is I can say drop everything between points for and last 5 by using a dash there, the same as the minus symbol. Stata will read this as drop division and all variables between PF and last 5. I click enter, and we're left with a small data set that I could probably just list and take a look at, yeah. Now let's see with the variables. I'm going to say list in 1 to 5 to just show me the top 5. And this is a good sample of what our data set looks like now. Now one thing you notice is that the team names sometimes have these prefixes on them. That is because I downloaded these tables from NFL.com, and they use these letters to denote conference champion, teams that make the playoffs, and I think division leader. I think those are the 3. Now this isn't going to matter if we're only looking at 1 year of data, which we are here, for the purpose of this example. But the data set does contain many years. And in the case that you're going to use all the data, which you will for the assignment, you want your team names to match up. So for example, if I tabulate the team name, and actually I don't like that variable NFL team. It's a little redundant. Let's rename that first. I'm going to rename NFL team to be just team in all lowercase letters. You can see over here, all it did was change the team name. It kept the same label as what it used to be called, but now it's just team. So I'm going to tabulate team, and you can see the problem here. We have a lot of teams with this prefix, and if I look at, for example, the Arizona Cardinals here with a Y in front of it, should have been when they were a division leader one year, that's not the same value as the Arizona Cardinals when they weren't the division leader. So Stata will not recognize those as the same team. Now, to be clear, that's not going to really be an issue in this assignment, but in general, you might want Stata to know that those are actually the same team. So we should clean this up. We've talked about how to handle strings a little bit, but this particular issue is handled well with a command called subInString, or at least that's what I call it. Pulling up the help file for this command we're going to use, you can see that what it does is it displays S1, and S here stands for string. That's how you read this in the syntax. It displays the string variable, or the string, that you write in this position. So you'll write subInString in parentheses. You'll put a value here. We're going to put a variable. It's going to display that variable, or the values of that variable, where the first in occurrences. So in is going to be a number here, and actually for us, we're going to set it to missing. In S1 of S2 have been replaced with S3. Okay, what is that saying? We're going to give it a variable. We're going to look for particular characters, S2. We're going to give it some characters we want it to find. So for us, it'll be those Z dashes and Y dashes. Then we're going to tell it another string and say replace those characters whenever you see them with something else. And we're going to give it an empty space. Basically, get rid of them. Don't replace them with anything is what we're saying. We're going to set in to missing, which means replace all occurrences. If we were to say, give it the number 1, we would just say the first time you find this in a variable, replace it. If we say 2, it'll say the first 2 times you find this character, replace it. We want them all replaced. And actually for us, it doesn't matter because each team will only have those characters once. So actually whatever you put here for this example doesn't matter, but in general, that's how you use it. So they give you some examples here. You can literally just type a string yourself instead of a variable. So this one, they typed the string, this is the day. The second option is, that's a string as well in quotations, which means we want to replace whenever this set of strings, these characters, whenever you see it, whenever you see is exactly, replace it with a capital X. The one here says, just do it the first time you find is. So you can see here, the word this had is in it, it was replaced with an X, but then it stopped. It didn't do the second one because we said, just do the first occurrence. If we change that to 2 occurrences, it replaces the first 2 instances of is. If you put a dot here or a period, which is Stata for missing, it will do the replacement any times it sees is. So here they wrote this is this, so now there's 3 occurrences. And you can see when they said replace it whenever you see it, we'll have 3 x's. So let's apply that to our case. So just looking here at the bottom, I see a Z dash that I want to replace. So just to show you that this is working and to be safe, I'm going to generate a new variable. Let's say generate clean team, because we're going to clean the data. And we're going to say that equals subInString team. That's our variable. So we don't have to write a string. We can write a variable and then it'll do it for every row of this variable. We're looking for Z dash, and we want to replace that with nothing. So I just wrote 2 quotation marks. It's a blank. It's not even a character, so it's not even a space. If it were a space, there would be a space, but this is blank for a string. And we want to do that whenever you find it. You could write the number 1 because there will only be 1 instance of that because no team name has a Z dash in it. All right, let's see real quick if that worked. I'm going to list these last observations. I'll say list team and clean team so we can see them together in, let's say, -5 and -1. Well, that didn't work. I wanted to see the last 5. Let's see, how many rows do we have? We have 320 rows. Let's try this again. So I will say, show me 310, row 310 to 320. I see what's going on here. I tabulated the teams. These are not in order. Well, I don't know where they are, I guess. Let's just browse the data. So I'm just going to browse team and clean team. There we go. So as you can see here, the Atlanta Falcons had a Z in front of them in row 5. Now they don't. So this worked as expected. Now that I know it's working as I thought it would, I can instead write the code to say replace the variable team with the version that has Z removed, because now I know it's going to give me Atlanta Falcons here. So I'm going to drop clean team because that was just a test. And now what I'll say is replace the values of team with values of team that has nothing substituted in for Z dash. And let's just browse that real quick. Or actually, let's tabulate team. No more Z's. We're looking here at the bottom, and there's no more Z's on these teams. So let's just repeat the same process for the Y dashes, and we also have some star dashes. That's Shift 8. Now, because I'm lazy, I'm just going to click that same code I wrote and replace the Z with a Y. It says 39 changes made. That's good. We expect changes. And now I'm going to replace the Y with a star. 20 changes. Now when I tabulate team, let's see what happens. Okay, we don't have any of those annoying Y's, Z's, or stars. There is one odd thing, though. Why is it that I have 10 seasons of Buffalo Bills and only 6 Cardinals, 6 Falcons, and 4 Ravens? Let's scroll down a bit here. These should be in alphabetical order. And you notice it starts over again at some point right here. Why is this Arizona Cardinals not the same as this Arizona Cardinals? Stata does not recognize those as the same string. This is another common error we get in data, especially when it comes from Excel. So what I'm going to do is I'm going to use the command carlist or charlist, and I need to give it a variable. This lists all the characters in a string variable. So if I write carlist team, as I should have done in the first place, it gives you a list of every character that appears in that variable. Now we see the issue here. These 2 question marks are symbols that are in Unicode. And unfortunately, they're Unicode symbols that are simply blank spaces, so our human eyes can't even see them, making things very annoying. You might think the .49 is a problem, but the 49ers are written here, as you can see, with numbers, so that's okay. And the dot is actually a period for St. Louis, I believe. Let's see. Yeah, St. Louis. So we don't want to get rid of that. That's fine. The 49 is okay. The dot is okay. What we're worried about is these Unicode characters. Now, what I'm going to show you is a bit advanced, but I want to take the time to do it because you might come across this, and then you'll be looking at your variables. And even if you try to edit them in Excel before importing them, you can't find what you can't see. So if this happens to you, which it might not, I hope it doesn't, here's an advanced thing you would want to do. First, there's a user command that was written by somebody, not Stata, but Stata allows it in the program, called chartab or cartab. So it's like car list, but it's cartab. If you don't have it already, which I do, you can install it by typing ssc cartab. ssc install cartab. So I get an error because I am not connected to the internet right now, but also I already have this. If you type ssc install cartab, Stata will connect to the internet and download the user written command for you. You can see here my error is it could not be contacted. That's because I'm not connected to the internet. Once you have cartab installed, you can read the help file, as you should, but I'll tell you that it's basically the same thing as car list. It just looks at Unicode characters as well. So if I use car tab instead, we get this huge list of every character, and each one has its own row, and it even lists the spaces and tells you their decimal representation and their hexadecimal representation. We're going to use the decimal representation. Now, a space is okay. Our team names do have spaces. The period, the 4-9, those are okay. All the letters are okay. When we go to the bottom, there's a different kind of space called no break space. That's the different character that we can't see with our eyes, that we want to get rid of. So we're going to identify that by the decimal representation 160 and tell Stata to get rid of it. Now, I give you in the PDF exactly what to type here because it is advanced. I don't expect anyone to figure this out. And so I'll give it to you right here. We basically use a different sub and string command where we put U in front of it. That allows us to handle Unicode characters. So this syntax is similar to what we just did above for sub and string. We're telling it we want to substitute a character in team. Here we're saying the character is a Unicode character, and it's Unicode character number 160. Everything else is the same. Replace it with a nothing, and whenever you see it, get rid of it. Because I literally don't know how many instances there are because I can't see it, so just get rid of them all. Once I do that, if I do my car list again, and remember to put team there, we have only letters, the period, and 2 numbers. Perfect. We have clean variables. How can we check this? Well, let's tabulate team again. And you can see I have 10 values of every team for 10 seasons, except for the Rams, which moved to LA. This is another common thing to deal with in sports economics. Do you want to call the LA Rams the same team as the St. Louis Rams, or treat them differently? If you want to count them as the same, you'll have to change one of those names so that they match all 10 seasons. Here we don't care about that, so I'm just going to leave it alone. Okay, so our data is a little cleaner. Again, this won't affect our calculations here, but these are common issues you might come across in your own research, and so I wanted to show you how I handle them. So let's start to take a look at our variable of interest, which is the winning percentages of the teams. That's what we use to calculate the standard deviation of the winning percentages, obviously. And then we compare that to the ideal measure to see if the league is competitively balanced or how close to the ideal league it is. So let's just summarize that percentage variable. And something you might notice is that the average should be exactly 0.5. For every winner, there's a loser. So on average, we should see a winning percent of 500, but we don't. What's going on here? Well, if you notice, we have the possibility of ties in the NFL. They are exceedingly rare, but here's one in just the first 10 rows. The Seattle Seahawks had a tied game in 2016. This will make our average percentage not exactly 500. For the case of this example, I want to give you a clean example without ties, so let's go ahead and get rid of all seasons with ties. And this is what you're going to do for your assignment as well. Now, how can we do that? Let's identify the seasons that have ties and those that don't. So first, I'm going to tabulate year. Make sure we have everything between 2007 and 16. Looks good. And then I'm going to tabulate a year if the variable tie is greater than 0. So what this is going to do is tabulate the value of year anytime there is a row where a team had ties that season. And we see there are actually 5 seasons with ties. 2008, 12, 13, and 14 both had, or all had, one tied game, so you'll have 2 values, one for each team. 2016 had 2 tied games, so there will be 4 teams with a tie value that's greater than 0. And as I recall, as somebody from Ohio, Cincinnati Bengals were always tying, or it seemed they were always tying at least once per season. So I want to know what teams these are, just out of curiosity. So I'm going to tabulate team if T is greater than 0. Yep, Cincinnati Bengals on top, 3 ties. We are the champions of ties. All right, so we want to get rid of these years with ties because that'll make our ideal measure a little less than ideal. Because if you've watched the video on the theory behind this measure, you know we're assuming that teams could only win or tie in an ideal league, and there's a 50% chance of either. We haven't worked in ties to that calculation, and so when we apply it to real-world data with ties, it's not going to match well. It's not going to be off by too much, to be honest, but it's not going to be perfect. So let's get rid of those seasons. Well, how do we do that? There's the easy way. I could say drop if year equals 2008, then say drop if year equals 2012. I could actually say drop if year is 8 or 12 or 13 or 14 or 16. Actually, let me show you many ways to do this. And before I do that, I'm going to drop these observations many times. So after I drop them, I can't Control Z. I can't undo that. I'll have to load the data again. So let me go ahead and copy down all of our useful commands into my do file so I can get back to where I started quickly. This is one of the beautiful things about having a do file. So let's see, what was the things we needed? Drop those variables we didn't care about. We rename the team. And what I'm doing right now, I'm on a Mac, so I'm holding down Command when I click these so that I can highlight more than one. We replaced the values of team. I know those three are ones I want to keep. Let me pull this out to show you what I'm keeping. You will already have the new command installed, so we don't want to do that again. Actually, we just want to replace. And I think that's it. So I'm going to now right click, send to do file editor. As you can see, it opened up a new one for me, but it copied them all over. That's nice. I'm just going to copy that and paste it into my original one. And I'll put a little note here saying data cleaning so I know what this code is actually doing. Okay, let's go back. Let me show you the brute force way to do this. I could say drop if year equals, and we'll use double equals, 2008. 32 observations deleted, which is good. There's 32 teams. That's what I expected. And now, if I tabulate year if there's ties, 2008 no longer appears because it's not there. If I tabulate year, we're missing 2008. You can see that. So I could do this. I could write this for every year. Right? I could even be a little lazy and just click here to copy over the code, change the year one at a time. Let's see, we got 14 and 16. Okay, there we go. So that's one brute force way to do it. And just to make sure we've got it done, we can say sum t, the tie variable. And as you can see, the maximum value of tie is 0. There are no more ties available. Each year, drop 32 teams as expected. Okay, that's the brute force lazy way to do it. By lazy, I mean lazy thinking. Because whenever you find yourself doing something over and over with code, there's an automated way to do it. There's always a better way. So let me go to my do file, and I'm going to run the script so we get back to where we started. So I click do. Oh, it says no. It doesn't want to write over the data that we changed. So what I have to do here is add an option to my import Excel where there's two things I can do. One, I could say clear, which gets rid of everything first, or I can use the option import Excel, and after the comma, I say clear, which is telling Stata it's okay if you're overwriting data. I click do, and that worked. So let's make sure we have what we think we do. Once again, I'll tabulate year if t is greater than 0, and we have the data back. Okay, we're back to where we started. Here's another way that I actually only recently discovered to refer to situations where a variable takes on many values. Here we want to refer to the situation where the year takes on value 2008, 12, 13, 14, or 16. So what I can do is use the command inlist. So I'm going to say drop if inlist, and then in parentheses I'm going to write year, comma, 2008, comma, 2012, so on and so forth. I'm going to list all the values and then close parentheses. So what I just told Stata to do here is drop if we have a situation where the value of year is in this list. So I provide a list of values, and basically what inlist does is it gives Stata a Boolean, a 1 or 0. And so if this is true, if for each row your value of year is one of these values, it returns a 1. And this says drop if that's true. You can see we lost 160 observations. If I tabulate year if ties are greater than 0, there's no more. So that's a very efficient way to do this. Now, I'll show you one more way that seems more complicated, but if you're dealing with a very large data set, it will be more efficient. So first, let's load our data again. Get back to where we started. Make sure I have my tide years, and I do. And we're going to use here the command calledegen.Egen is the same as generate, or what we often abbreviate as gen, but E stands for extensions. So this is a list of complex generate commands that many people want to use but weren't included in the original generate command. The one we're going to use here is total, the total option. So let me search for it. Not row total, total. There we go. So we're going to use this total option. And as you can see here, it creates a constant within the variable list containing the sum of whatever expression we put in here and treats missing as 0. So what total is going to do is it's going to look for all cases of whatever expression we're writing here is true, and it's going to give us the total amount. So let me give you an example. If I writeegen test, so I'm generating a variable just called test, it's a variable name, equals total, and then parentheses I'm going to write t greater than 0. This generates a variable called test that gives us the total number of times that this variable t is greater than 0. Now if I list the first 10 observations, you'll see that it's 12 for everybody, or for each row I should say. That's because total t greater than 0 simply counts how many times there's a tie. That number's 12. And so what I really did was I just said generate a variable called test that's equal to the number 12. So that's what it did. Now this is going to help us identify years with ties because this gives us a single number for the whole data set. What we want to do is we want to do this separately for each year. Now you've already learned how to run commands separately by values of a variable, and that's by using the command bysort. So we'll say bysort year, colon, and that's telling Stata, hey, I'm going to give you a command, do this separately for each year. Egen test equals total t greater than 0. Oh, we already have test, let's drop it. Or should we just rename this something else? Let's just name a different variable. Let's call this variable ties. Now let's take a look at our first 10. Our first 10 are 0, and that's because in 2007, there were 0 ties. When we use bysort year, Stata does this command, or whatever we write after the colon, separately by year, so we're generating the total number of ties separately by season. Now I remember 2008 had ties, so let's do this. List if year is 2008, and as you can see, the value for ties is 2, because there were 2 ties this year. We should be able to find them. Philadelphia Eagles, and of course the Cincinnati Bengals. They love tying. So now we have a variable that will tell us the number of ties, and it will say 0 if they don't exist. So this will help us identify entire seasons, not just a row, but entire seasons where a tie occurred for some team. So what I can do here is I can then say drop if ties greater than 0. And once again, you see we have the same 160 observations deleted. There are no more ties. We can summarize T to make sure that's the case, and it is. So I've shown you many ways to identify entire seasons we want to drop, many ways to do so. This last method is very useful when you have a very large data set. Imagine you were doing, 100 years. Do you really want to type all those years into drop by hand? No, you don't. So in cases like that, when you have big data, these are tools I use often, not just in sports economics, but in everything I do, to clean the data down to what I want, to identify entire groups of data where if I have one issue for that group, be it a season, be it a team, if I want to drop the whole group of data whenever one issue arises, this is the method I use. Okay, moving forward, Let's go ahead and compute the standard deviation of winning percentages, which is our competitive balance measure, for just a single year. I will leave it up to you to figure out how to do this for all the years without ties. So let's just take the first year, 2007. So I'm going to say keep if year equals 2007. Now if I tabulate year, we only have one. If I tabulate team, we have one team observation for each team, 32 teams. So everything looks as expected. Now the first thing you should notice is the variable PCT is still not exactly 0.5, even though we don't have ties. What is going on here? Well, if you notice, the variable only has 3 decimal places. This is because I copied it from NFL.com. They don't display an infinite number of decimals. So these are actually rounded to the nearest third decimal place. We want to get precise measures because our mean should be exactly 0.5. We're in the business of precision, right? We're data scientists. So what we want to do is calculate the percent ourselves, because we can do that just by dividing the wins by 16, which are the number of games, and we're going to use double precision. So what I'm going to do is I'm going to say generate WPCT for win percent. And actually, before I write the variable name, I'm going to write the word double. I'm going to say generate double WPCT equals wins divided by 16. Now what I did there is when you type double in front of the variable name, you're telling Stata, I want this to be a double precision variable. That's the most precise data storage we have. I think it's 16 decimal places. So if I describe WPCT and PCT, actually PCT is double, but again, I copy and pasted this from NFL, so Stata thinks that the value is exactly 0.563 when it isn't. Here we generated it ourselves by dividing W by 16, so let's take a look at the difference now. As you can see, that 0.563 is actually 0.5625. Small difference, right? But these small differences are errors in our calculation, and they're unnecessary. So now if I sum our version of percent, you see the mean is exactly 0.5 as it should be. The minimum is 0.0625. Wow, that's quite low. And the maximum is 1 for the perfect season of the Deflatorgate New England Patriots. All right, now let's calculate our standard deviation by hand to make sure we know what we're doing. Is this necessary? In general, no. For a student, yes. You should always check your understanding by doing things by hand the first time. Looking at the PDF, what we're doing is we're going to recreate the standard deviation variable. We're going to take the win percents we just made, subtract the average, which now we've identified correctly as 0.5. We're going to square that for each team. We're going to add it up over all teams, T, so that will be 32 here, and then divide by 31, or T minus 1. This will give us our standard deviation for the year of 2007. So we just made this variable. What I'm going to do next is make a variable equal to 0.5 for everybody. We'll take the difference, we'll square it, add it up, divide by 31. Okay, so I've already identified that the mean is equal to 0.5. So I could generate, let's call it W bar equals 0.5. And if I do that, you see that that's going to equal 0.5 for each observation. So we could subtract each row's winning percent or each team's winning percent from that, square it, and then we'll add up all those values. But actually, I'd like to show you one other thing you could do here if you didn't want to enter this by hand. Or if this value was something with a lot of decimals that might not even display in Stata. They might not display all of them here. Whenever you run a command, there are stored results. Stata is displaying to you here the number of observations, the mean, the standard deviation, the min, and the max. These numbers are stored as constants right after you run this command, summarize. You can access them or refer to them, and each command's help file will list how to do so at the bottom of the help file. Let's take a look. And we want summarize. So if I go to the bottom of the help file, you see here stored results. Summarize stores the following in R. What we want to access is the mean. So immediately after using the command summarize and before using any other commands, if we want to refer to the mean value that was displayed, we just need to type r parentheses mean. So let me give you an example of why we might want to do that. Instead of generate w bar equals 0.5, we could say generate, I'll say w bar 2, we'll make another one, equals r mean. Now before I do that, let's make sure that we have the stored results. Let me summarize again, because I think using the command generate might have overwritten these stored results. So I'm going to summarize wpct again, and then immediately afterwards I'm going to say generate w bar equals r mean. Oh, we already have that, w bar 2, I'm sorry. And now if I look at the first 10 rows, I should see it knew exactly what to put here because I'm referring to the mean that was displayed here. Oh, and now that I think about it, we should go ahead and make this double precision as well. So I'm going to drop all my W bars. Let me do this one last time. Gen double W bar equals R mean, the mean value that we just saw. Ah, here it says missing values. This is exactly what I was talking about. It didn't give me anything. Why? Because right before I generated this, I used the command drop. And so since my last command wasn't summarized, it didn't have that stored result. Let's do this one more time. Summarize winning percent. Oh, we gotta start over. Drop W bar. Summarize winning percent. There we go. Now generate the double W bar equals R mean. Finally, we have it. There we go. Now you might say, what's the difference? It was already equal to 0.5. Stata is displaying 0.5 to you, but it might be storing the number as 0.4999999, and so on and so forth. It might store the variable as 0.5, a bunch of zeros, and then a 1. Not all numbers can be stored perfectly in binary, which is what all information is stored as on your computer. So this is why we want to use double precision, because if there's any tiny rounding errors, they will typically not be displayed to you here, so you won't see them. To guarantee you have the most precision, you always want double precision for your numbers. All right, so next up, we want to take the difference between those two and square it. So I'm going to generate another double called square diff, sqdiff, which is going to equal the winning percent minus the average, and in parentheses, I'm going to say square that. And just like online calculators, you'll use a caret for an exponent to tell Stata to square this value. And let's take a look. Looks pretty accurate to me. You can see there's a ton of decimal places because we're making this a double precision variable, as we should. Now what we want to do for our season measure is add up all those square differences. We want to add all this up for all 32 teams. Well, we just saw how to do that with egen. We can use the total option. So I'm going to say egen double. Again, we want double precision. Let's call this numerator because it'll be the numerator of our standard deviation equals total, that's square diff variable. Now when we list, we see it's giving us the same value as it should because it's just adding up all of these square differences. It's the sum of the square differences. Now our denominator is going to be t minus 1. We have 32 teams, so that'll be 31. So lastly, we can generate our double S for standard deviation equals the numerator divided by 31. And lastly, we'll list these values. Oh, you know what we forgot to do? We forgot to take the square root. That's my bad. So let's replace that S equals S to the 0.5. We have to take the square root. That's why it was looking weird. And now we have our standard deviation of winning percentages for the year 2007 in the NFL as precise as possible. Now it's good to calculate this by hand so that you know what's going on and you have this memory of doing it yourself. But of course it's unnecessary here. If I simply say sum WPCT, we get that standard deviation right here. But as you can see, ours is a bit more precise when it displays here as a double precision variable, but these are the same number. This one's just rounded. Now what's another way we could have done this? Obviously we can refer to this stored result. Let's do so right now. I'm going to generate double. Let's call it S2, the second version. And all we have to say is R and in parentheses SD for standard deviation. Now take a look at these. They're the same number. A third way you could have done it is with EGen. EGen also has an SD option. So we could have said EGen double, I'll call this one S3, equals SD in parentheses winning percent. So this is saying generate a double precise variable, we'll call it S3, give me the standard deviation of this variable. Now if I list all of these, oh, that's a different variable. Let me do this again. List S1 through S3. We didn't have an S1, sorry. Let's do this the brute force way. List S, S2, and S3. That's what we want. You can see they're all the same. So once again, 3 different ways to calculate this standard deviation. But notice that the reason why Stata gives you the exact same number, whether you use EGen or summarize to the one we calculated, is because we use double precision variables, which is the same thing Stata will do. So when you do either of these commands, Stata is essentially doing everything we did to create this variable, and then it's dropping all the intermediate steps. So if it creates any temporary variables in the background for the difference between the mean and the winning percent for each team, and then squares it, it'll drop all that information and you never actually see it. Okay, so we have our standard deviation. It doesn't look close to what it should, if you recall what the ideal standard deviation of the NFL is. I'm not going to tell you here. I want to make sure you watch the video or read the book and look it up yourself and know how to calculate it. But there's a great way we can test if the standard deviation of our winning percentages here is equal to that ideal. And that's a command called SD test. So if you look up the help file, it's a comparison of variances. This test will test whether or not the standard deviation of your data set is equal to some number. So we're going to use the first method. We have one sample, one season of NFL data. We want to test if the standard deviation of our winning percent, so for var name we're going to put in here winning percent, equals the ideal number. So I'm going to do a silly test. I'm going to see if it's equal to the number 1. Now this is not the ideal standard deviation for NFL. I just don't want to give away this part. I want you to calculate that by hand or watch the video. But let's say it was 1. We would just simply write SD test W% equals 1. What we're doing here is we're saying test if the standard deviation of this variable is equal to 1. And we want to compare that against the alternative, HA, the alternative hypothesis, that the standard deviation is not equal to 1. Down here we see that our p-value is essentially 0, which means that the standard deviation is different from 1, and there's essentially a 0% chance that that's due to randomness. The reason why our calculated variable is different from 1, this right here, is because it's actually different. It wasn't random. So all of you should know about hypothesis test from your probability class. This is just a simple hypothesis test that some number, the standard deviation, is equal to some other number. Now for you, you're going to want to plug in the actual ideal for NFL and test whether or not the standard deviation we get for our winning percent is equal to the ideal number, which is not 1. Again, it's a different number that I want you to come up with. Okay, another thing we can do with competitive balance that is fantastic for exploring data, for visualizing what's going on, is we can compare the distribution of winning teams, or their winning percents, to the ideal. So let's start doing this. I can make a histogram of the winning percents simply by typing histogram WPCP. And when you do that, Stata will quickly generate this histogram. So the x-axis is the winning percentages. The y-axis is the density, or how many, what proportion of teams fall into each category. Stata automatically decides how wide these bins should be. You can change that in the options. So if you look at the help file for histogram, you can change how wide the bins are. Here they're quite wide, but we get the general shape. And something I like to do, I don't like displaying this as density. I like to display this as percentage, what percentage of observations are in each bin. The shape won't change, but the scale does. So what I always do is say histogram And then I say comma for the option percent. Oops, mistyped it. There we go. So this is a lot easier to read for me because what it says here is if you look at, for example, this middle group of teams, they comprise a little over 40% of the total sample of all teams in 2007. That's a lot easier to interpret, so I use the percent option. Does this look competitive? That's the question. Well, 0.5 is here. It looks like the average is around 0.5. It's a little skewed. But what should we do? Well, we should compare this, perhaps, to what the ideal would look like, what we expect. Now, one way to do that in a continuous manner is to use what's called a two-way graph, which a histogram is a two-way graph, but plotting a function. We can plot a math function. Now, this is a bit advanced, so I've gone ahead and given you the code for this. I don't expect anyone to learn this. We're going to plot a two-way graph, meaning 2 dimensions. We're going to plot a function, y equals the normal curve, this normal density. Give me the normal curve because, again, we expect those winning percents to be distributed approximately normal. X represents the X variable. We'll actually just leave that as X. Mu is the mean that we want this distribution to have. So for us, it'll be 0.5. Sigma is the standard deviation that we want this normal density to have. So for that, we'll plug in the ideal standard deviation. And I guess I am going to give it away here because I have to type it. So the ideal for the NFL, you should have watched the video or read the book, is 0.125. The range is going to go from 0 to 1. And what I've done here is specified that I want a medium thick line. This is just an option to make it look a little nicer. So let's see if I can copy that, paste that into Stata. I paste that into Stata. I'm going to replace mu with 0.5. I'm going to replace that standard deviation with 0.125 and see what we get. There is a perfect function of a normal density with a mean of 0.5. This is what our ideal distribution of winning percentages should look like. Now we can plot this on top of the histogram by doing 2 ways at the same time. Two ways. So I'm going to say 2-way, and then in parentheses, I'm going to write that same command for my histogram. Oh, that didn't work. I'm going to put that in parentheses, histogram, and say 2-way in front of it. So I'm going to say do a 2-way graph, do this histogram, and then in another set of parentheses, I'm going to copy this command and put that in a different set of parentheses. So that's going to plot the histogram, and then on top of that, the normal density. Oh, and that doesn't look good. You know why? Because I used percent for the histogram and not for the normal density. Let's do that again. Let's see, can I use percent for normal density? We'll find out. Let's write percent. Nope, we cannot. So what we'll have to do here to compare the two is get rid of that percent option we used for the histogram and just use density for both. There we go. Well, as you can see, it generally fits the ideal distribution, but there's a bit more density on the right than what we would expect. As I said in my video, it should be very rare we get a team that wins all their games, but we did in the season. Now, I know what you're saying. It's because Brady deflated the footballs. I got it. But it did happen. It's in our data. But again, maybe that goes to prove the point, right? If we had a perfectly competitive league, you wouldn't have one team deflating footballs and cheating to win. So clearly, we're not going to have a perfectly competitive league in this year. But this is a good comparison of our data to the ideal. But yet another way I like to look at the data is instead of comparing these histograms to this smooth continuous function, I like to take this histogram and generate the smoothest function that looks like it represents it and display that instead. Because here we're really comparing a discrete distribution to a continuous one. So that's going to give us some error anyway. So what we can do then is replace histogram with something called a kernel density. You can type K density. A kernel density basically takes that histogram and fits the smoothest line that seems to represent it. You can read up on the help file how they do that. It's a little dense in the math, but Essentially, it's just drawing a smooth line over the histogram. Now, when we do that, these are a little more comparable. The blue line now is the kernel density of the winning percent, which is a smoothed function that seems to represent that histogram fairly well. And the red line is our ideal that we would expect if this league was perfectly competitive. So obviously we're missing a lot of density. We're missing a lot of teams here in the middle. We have too many bad teams and too many good teams compared to what we would think of as ideal. Now again, we're just doing this for one season. If we threw in the data for all seasons, without ties, let's say, and calculated this number, we might get something closer. We only have 32 observations here. If we did all 10 years, or all years without ties, I think maybe there were 6 of those. Well, in any case, we would have a lot more observations. This blue line might be smoother, might not be as clumpy in certain areas. What I'm going to ask you to do is to calculate the standard deviation of winning percentages separately for each year. So you'll have a different number for each year. But to calculate the standard deviation of the entire data set, you could just do it for all years at once and have a single number. The benefit of doing that is you have more observations. Each team year is giving you an observation. But remember, in that case, you need to divide by the number of observations minus 1, which will not be the number of teams. Here they're the same thing. We have 32 observations, 32 teams. If you do multiple years at once, you got to divide by the total observations minus 1, which is not the same thing as teams. Okay, so that's a lot of information, but a lot of good tools you've just learned. So now it's your turn to go out there, recreate what we just did here for each season that does not have ties. And then, if you would like, for extra credit, go out and take data from another league, preferably one that doesn't have ties. You could do MLB, you could do some obscure sports league I've never heard of, just something that has wins and losses only, and see how competitively balanced the league is for a given year, and write up a short explanation. All right, have fun.